backgrounds in terms of what everybody's looking for and what everybody's into. That's really good to hear. So I guess we should probably start getting the ball rolling. So what is this course? It's kind of two parts I'm going to do here. The basic ham course. So for those who are reading along, read their textbook, you've already read chapter 1, I hope. Chapter 1 kind of outlines what you're allowed to do with the basic, right? So the basic operating license gets you to be essentially an appliance user, right? You're not going to be able to build anything in radio. You're not going to be able to use it on the ham bands, unfortunately. That's because most of the basic is geared towards legal requirements that you have as a ham and some basic mathematical theory. The good news is you don't have to learn a lot of advanced electronics in order to get your basic ticket. But I know some people come in thinking that, at the end of their basic ticket, they'll be able to build thousands of dollars worth of radio gear. And unfortunately, it's a lot of learning. This course is going to be broken up into 3 components, though. So the first one, what it isn't unfortunately going to be a general introduction to radio. Radio is a massive, massive field. And I mean, even any of the guys who are here as instructors, would you say you've known like everything in radio, or that you stick to a small portion of it?
Everybody stays to a small portion and experiments outside that a little bit.
Yeah, exactly.
As in, the 3 of us should be able to cover a fairly big area.
Hopefully, yeah. Yeah, I mean, for example, my real reason of getting into this is more of like the tech side. So I come from a computer science background. I don't even touch anything below 30 megahertz, which is HF, right? So there's lots of areas that I haven't been a part of, and no matter how long I'm in this hobby, you can't understand everything. So unfortunately, it's not going to be what some people are hoping it is, but hopefully we can get enough to meet everybody's needs for being here. Next one. So the structure of the course is in 3 parts. We have the book, the online, and the in-class. Okay, and each of these, initially I was trying to make them all one and the same, so that you were taking the online course, you were doing, the in-class course, you're going to be doing the reading. That's probably the wrong approach to take. There's just so much material you have to learn, and it depends how much material you want to learn, right? I mean, if you're here just to get your basic license, you want to start talking on the radio, those requirements are a lot simpler than if you're trying to get into this hobby to learn a lot about the math, about how radios work, if you want to go for your advanced ticket per se. If you have a career in radio and radio design or electronics design, there's much, much more material than we can actually cover. So the book, perfect. The book is going to be sort of what we consider the medium depth on the topic, all right? It has a very well-structured lesson plan. It begins with electronics theory and works you towards the law, specifically because the test is mostly law. And so the idea is, because it's very little electronics, you have to do all the electronics theory first, so that by the time you've forgotten it, you've got most of what the test is on, and you still have that sort of core foundation you're going to need in order to work through the test, all right? This is in contrast with the online portion. I know some of your names from the online portal. We get to see all the students that are in there. Who has signed up for the portal? Cool. And who hasn't? Okay.
What are we talking about, the portal?
So the online learning center, there was a link that was sent out, I believe 0.9 in the introduction email, that talked about the course that you should sign up for online. The main reason is because it's going to be the in-depth version. So what we're doing is I'm going to be breaking down every single topic we have. So for example, one of the topics is resistor coloring, right? You have to just simply memorize the way resistor colors work. So the textbook is going to give you a chart, right? And they're just going to say, well, you have to memorize it. The online portion instead is going to re-explain it, come up with different ways you can memorize it, give you reasons why we use it, lots of videos, lots of explanation. One of the examples I would want to point to is batteries, for example. We have 3 videos on there on batteries, despite there only being 2 questions on the entire exam on batteries. So it depends. If you want to learn a lot of information, that would be the resource to go to. So if you're getting confused about, well, we have to learn decibels, for example, and you're like, well, I don't understand how decibels are working. There's a 20-minute video on there that goes into more detail than anybody on the face of the earth needs to know about decibels. But it's there for you as a resource, all right? So occasionally when you feel you're not getting enough information or you want more information on a particular area, because again, everybody has their own interest, definitely check the online site. Finally, we have the in-course. So the in-class delivery, myself and Jeffrey and Bob, we were sitting around together, I don't know, less than a week ago, Wednesday? Yeah. We were sitting around Wednesday, and I produced a whole set of slides for this that was going to essentially cover topics in chapters 1 through 3. It was going to reteach everything that the textbook did, and we felt, okay, let's take a look at the exam and actually what you're going to be tested on. And we were going through the questions, and we were like, and we thought, okay, in class, we only have technically we have 16 hours, but 3 of those are for the exam, and we're going to probably have a half-hour break, and that's a maximum. So maximum 15 hours in class. We can't reteach everything the textbook's teaching and everything we have online. So the in-class portion is going to be specifically exam preparation, okay? The format I'm going to work with this is we're going to be pulling actual examples out of the exam. We're going to first present them in the hopes that you've done the reading. You should, theoretically, if you were doing this a self-study way, you've read the textbook up to that point, you should know the answer to it. We're going to let everybody read through the questions. We're going to do a sort of who feels this answer, who feels this answer, who feels this one, reveal the correct answer, and then we'll go through a detailed explanation as to why that particular answer is correct. So in case you've used the wrong formula, if you just didn't remember any of that portion, all right? We feel this is kind of the good approach because then you have the surface level, the medium level, and the in-depth, right? And you can select which in every particular topic you feel you want or need, right? Hopefully that meets everybody's expectations. If it's not what you were hoping for, unfortunately, we had to try and make a decision, but we felt, again, because the instructors as well, there were a couple of questions, specifically one, and it's in the slides we'll get to. We argued for about 30 minutes as to how the question was completely wrong, and then we eventually figured out, no, it was completely correct. They're chuckling because they remember it, and we'll get there too, and hopefully it throws the whole classroom for a spin, but that'll be fun. Format of the course, 8 weeks, 3 hours a night. I say 3 hours a night because that's the maximum. I'm hoping to get around the 2-hour mark with a half-hour break in between. I would hate for the class to run on indefinitely, but at 9 o'clock we will cut it off. And any questions we didn't get to, if we feel they're important, we'll throw them in the beginning of next week and just try to move a little bit faster. So you can guarantee you're out of here by 9. The cost, $50. The main thing that's here to cover refreshments and the exam. For the examination, our club doesn't actually have an examiner right now, so we have to pull in another examiner from another club. The way you probably read the exam works, the exam is technically free, but if you do it with Industry Canada, they will charge a fixed rate of, I believe, $20 or $10. I can't remember exactly which. Amateur examiners are allowed to set a fee that's agreed upon based on what everybody agrees on, mostly to cover their costs. They have to print like 10 or 15 pages of text, and they have to sit there for a couple hours. So we'll be getting in an examiner for that. That's going to pay their time. As well, this gets you an NSARC membership. I don't have membership forms with me this week, but after you've paid your thing, you're totally welcome to sign up for a year. You'll be covered for the 2017 year, which is essentially September 2016 until June 2017 or July. I can't remember which is our last meeting, but that covers you for that full year. So everybody, once you paid up, that's absolutely yours, as well as cookies and coffee. So those are being greatly provided because my throat's going to get parched, and I'm sure you'd like a nice little bit of refreshment and a sugar boost. So, all right, again, NSARC membership. I don't have the forms with me this week, but I will get them to you next week. Absolutely. So this is the breakdown. Beside it is each of the chapters that we're going to be expecting kind of to be covered. The first one seems like a lot, it's not. The first 3 chapters were kind of assigned for this week. If you got the introduction email, you should have gone over them. If you haven't, don't worry, but make sure you catch up by next week. Chapter 12, Section 1 and Chapter 12, Section 2 are Q codes and the phonetic alphabet. You will constantly be memorizing those for as long as this course goes on. Every week's homework will include that. You just have to memorize them. There is no way around it. And Q codes, there are a lot of Q code questions on the test. Why we still use Q codes and why you're being forced to learn them. Technically, you're only supposed to use them in CW, but digital is a semi-CW language. So you can use them there. You should not use them on voice. We'll be going over that a little bit later. But again, you just have to know them, and lots of people who take their tests will end up screwing up 1 or 2 of those questions because they'll be like, it's QRA, and you have to know what it means. So, and Appendix 1. Appendix 1 was just a math refresher for anybody who, it's been a while since they've sat in an elementary classroom and learned about, multiplication, division. I'm guilty of it too, don't worry. Computer science, we don't exercise our math skills enough. So, anyway, in the following weeks, we'll be learning just AC and propagation. We'll be doing advanced electronics. Your amateur station is mostly going to talk about, actually, if you want to buy your first radio, what to look for, features, different protocols and stuff we use. And then finally, we have to dedicate 2 weeks to law, because as I said, the basic certificate is mostly a law test. It's, where can I broadcast, where can't I broadcast? Can I use this much power? Can I use this much power? So we have to spend 2 weeks on that. But
Unit number 4 is missing.
I misnumbered them. Okay. 1, 2, 3, 4, 5, 6, 7. I'm also missing a week too, so this will change. Absolutely, this will change because we're missing a week. So don't worry about it too much. The homework will be assigned at the end of this week, so you'll know what to read up on, and then I'll fix this up, and we'll be good to go. So, moving on. So the exam, if you've probably read ahead, you probably know that it's 100 multiple choice questions. The question bank is 1,026 questions or 20, I think it's 20 something. You can download them, you can read through all of them. If you have a memory like, I don't know, an ironclad wall, memorize them, go for it. Don't bother memorizing 1,000 answers. That's a little bit too much. So what we're going to be doing is we're going to be going through the exam, essentially, giving you the answers that you should be looking for, but we're not doing every question. We couldn't, again, cover 1,000 questions no matter how many weeks we, well, I mean, okay. If we took you all year, we could probably go through all 1,000 questions, but we're picking particular ones because most of the questions are permutations of each other. So it'll say, you know, okay, you're given the voltage and the current. Well, then what's the resistance? Well, you're given resistance and current. What's the voltage, right? And they'll do these sorts of like, well, we just change this number, change that number, reword these things, and it's the same answer. So we're going to be going through particular ones that express each of the ideas without covering every question in detail. Since you have, you're not learning, and if you're not learning, well, why come out, right? So, okay, to begin with, practice of the phonetic alphabet. Who here has studied the phonetic alphabet? 1, 2, 3, 4. Little bit? 5, 6? Okay. So I'm going to be asking you guys. I won't keep pressuring you guys, but like, you should know this. No. So, next slide. The way this is going to work, we're just going to go person by person, each person doing the next letter in this particular sentence. Oh man, I can't remember what this is called, but it's a particular sentence that uses every letter and also every number. Because numbers technically aren't important, but you should still know them. So.
That's the Fox test, believe it or not.
Oh, the Fox test?
That's
Okay.
what we use in telecommunications for
The
centuries.
teletype.
Yeah.
Yeah.
All right, so I'll go first with T being tango.
Where are we starting?
I know
TH.
tango.
Henry?
No.
Hotel.
Hotel.
Perfect.
Yeah.
All right. E.
Oh, E. I knew hotel.
Everybody knows the other guy's answer.
Yeah. E, that's a good one.
What it is.
Okay. It's echo.
Echo.
Echo. All right. Q.
Quebec.
Quebec. Perfect. Excellent. U.
Uniform.
Uniform. Excellent. I.
India.
India. I guess we'll go back to Glenn and then we'll go forward.
Charlie.
Oh, okay. Charlie. And K.
Okay. Got me on that one. Kilo.
Yep. Excellent. Kilo. Kilo.
Yep.
So let's get the instructors in here as well because I don't want you guys to get rusty. So B. Over to you, Bob.
Bravo.
Bravo. R.
Romeo.
Thank you.
Don't worry. Don't worry.
That really wasn't fair because my call sign's Romeo Tango Victor, so I should know Romeo.
What about O? O isn't in there. O.
Oscar.
Oscar. Okay. W is whiskey.
Whiskey.
You've got N.
Nora.
November.
November. Yes. Yeah.
F.
Foxtrot.
Foxtrot. Excellent. Excellent. O.
Oscar.
Oscar. We got X.
X-ray.
X-ray. J.
Juliet. Oh, sorry. I thought you were pointing at me. Sorry.
No, it's no problem. Juliet. All right, we'll head back on over to Tom. Or Bob, sorry.
M.
Okay.
What are we at?
U.
Oh, you. Sorry.
Oh,
Uniform. Yes, right.
yes, that's right.
Uniform. Yeah. M.
Mike.
Mike.
P is Papa.
E. Over to you, Jeffrey.
Oh,
E.
Echo.
Okay. D is Delta.
Oscar.
Oscar.
Victor.
Victor.
E. Echo.
Echo.
Romeo.
Romeo.
Tango.
Hotel. Oh, sorry.
Sorry.
Don't worry. Back up to you, Glenn. Yeah, you're on E.
Where? E?
E.
Echo.
All right.
Lima.
Over to you, Jeffrey. A.
Alpha.
All right. We got Zulu. Z.
New Zealand. What?
Y.
Think Donald Trump.
Yankee. Yankee.
Yeah.
That's excellent. All right.
I was trying to think of that.
Yeah.
It's broken up in the book. Yeah.
Yeah.
Okay. We got D. On over to you, Glenn.
Delta.
O.
Oscar.
Oscar. G.
Golf.
And S.
Sierra.
Okay. B.
Beta. No, Bravo.
Bravo. We're doing phonetic, not Greek. Anyway, A.
Alpha.
Charlie.
And Kilo. All right, I guess we'll do numbers. So these ones are really simple. There's only 2 curveballs.
1, 2, 3.
Tree.
Tree.
That's one of the first couple. It's not three,
Tree.
it's tree.
I hope it's 4.
Forward, yeah.
Okay, good.
5 left.
Fife.
I don't remember this, but I'll assume 6.
6.
It's still 7.
Yep.
Still 8.
And niner.
Niner.
So the last one being 0. So
So 3 is tree, 5 is fiver,
fife.
fife, and 9 is.
Niner.
Oh, okay.
Yeah. So I guess 3 kind of. As I said, 4. If you just say 4, most people won't catch. So you've messed it up. Or 5. Sorry. So, all right. Good to know. We'll be doing that exact same thing every single week. So if we brush up on it, we can move faster. So this is what I'm talking about when we're going to be doing the questions. All right. Each of the questions are broken down on here. The first is the section that you should refer to if you feel you haven't got the question quite right. You're not really sure what the answer is doing. Read over that section. There will be 2 versions on sections where it's changed between version 8 and version 9. Follow it appropriately for yours. You'll see it when we get there, and I'll just point it out again. But this is the first question. So, what is the most FM power transmitter, FM transmitter power a holder of a only basic qualification may use on a 147 megahertz channel? We have 1,000 watts, 200 watts, 250 watts, 20 watts.
It's 250 watts DC input.
Perfect. Yeah. So if we go to the next slide. Exactly. All right. Next one. Why? All right. So with only a basic qualification, this is basic or basic with honors. You're only allowed 250 DC watts input. All right. They don't work on peak envelope power or anything fancy like that for basic. It's just how much power your actual unit is rated for. Again, basic, you're more of an appliance user than you are a radio technician. So that's the way they're going to set it up for you. All right. Yes.
Can you explain, so that limits you 250 watt DC input power. What does that limit you to as opposed to an advanced qualification?
Okay. So the advanced qualification would actually allow you up to 1,000 watts peak envelope power. 1,000 watts peak envelope is just a way they measure the actual energy off of the antenna. The watts DC for the basic is basically your transmitter will be rated in a number of watts that you're able to transmit. So for example, I have a handheld that can do 5 watts. I can also do 1 watt or half a watt. And I have a mobile station, that's just one I put in my car, that can do 20 watts, 10 watts, or 5 watts. So if I have one that says anything over than 250 watts, I cannot touch that. I also can't use an amplifier on the output to increase it past the amount that it's set up for. So, or sorry, not the amount that it's set up for, but I can't increase it beyond 250 watts. So.
When you say input, it says you're saying input power.
Mm-hmm.
How's that relate to the output of the antenna?
So it's directly set up for whatever their particular antenna is. I guess I'll jump over to you guys.
Input power is the input to the final amplifier of the transmitter, and the transmitter is normally about 50% effective. So the output power would be about 100 watts. Out to the
A lot
antenna.
less, yeah. And the amplifier is called a linear.
Well,
So
why do I want to
if
sort of a linear
if
unit?
it is linear.
Yeah, that's what they talk
I
about.
say
Okay. Our next question, keep ourselves rolling here. All right. So this is where I was talking about the dual sectioning. So they've updated it clearly in the version 9. They've rolled back that position to 1.2, and 1.4 is where it is in version 8. So again, I'm not going to jump into that anymore, but if you do have different manuals, you'll be able to look at that. These slides will be available on the online learning site after the course. So feel free to pull it up once you're done, refresh your memory through it. So, which of the following statements is not correct? So for anybody familiar, this means that you're going to immediately assume one of them is. Radio telephone signals may be retransmitted in the 21 megahertz band when receiving in VHF band from a station operated by a person with only a basic qualification. In the 29.5 to 29.7 megahertz band when receiving a VHF band from a station operated by a person with only basic qualification. In the 50 to 54 megahertz frequency band when received from a station operated by a person with only basic qualification. In the 144 to 148 megahertz frequency band when received from a station operated by a person with basic qualification. Number 1? Okay, oh sorry, I thought you had something. No, it's cool.
No.
Number 1?
Yeah.
Okay, so let's see what we got. Okay, why? The only basic qualification without honors, one is not permitted to operate below 50 megahertz. So 50 megahertz, for anybody who's wondering, that's considered HF, high frequency. Can't operate that below without your privileges as an honors. Honors, again, if you score 80% or higher. You have to score above 70, so we're all aiming for honors, obviously.
Yeah, absolutely.
So, did you say it's the basic is 70?
You have to score
Okay, 'cause
70%.
it used to be 60.
It used to be, yes.
Okay, so it's now 70. And the honours is 80?
80 and above.
Okay.
Yeah. Back when it
There
was
you go,
60,
Jackie.
if you're...
Got to get 80.
Well, exactly. Back when it was 60, having that 20% gap was kind of like, well, just aim for basic and I'll upgrade to an advanced or I'll get the, whatever later. Now that it's only 10%, I mean, just work just a little harder, get yourself over the 80 and then you don't have to worry.
Why?
Which?
Why would we, why do we want to operate below there?
So, okay, yeah. One of the main things is a lot of hams consider HF to be like the holy grail of working. The reason is HF frequencies are much longer, so they travel much greater distances on lower power. The other thing as well is HF is typically where you're going to be using a lot of power, so you'll be able to make...
HF is below that.
Yes, HF is below that. So that's where you'll be able to make more international contacts if you want to talk to Europe or Japan or those sorts of countries.
So we're limited to the distance we can
Exactly, yeah. Yeah.
transmit.
So,
Just really quickly, with the qualifications for ham nowadays, because I went through it, it was different. Is there still 5 word a minute Morse code test like there were a few years ago?
There is not.
It's totally gone.
it's totally gone. So you can still get the 5 words a minute. It doesn't actually do anything here in Canada, but we still have it for reciprocal operating agreements. So some countries, if you go to, they will still on their test have a CW requirement, and in order to operate in their country, you may actually have to get it.
It's on this test.
No.
Yeah, on the review, if you go in and review under the coax publication, they ask you, and there's, all the different numbers of CW that you need to pass, and it says 5 is the answer.
No.
No, it doesn't say you have to have it, it just asks you what it is.
No, it tells you if you don't, in publication, if you don't pass with honors, you may do the
Oh, yeah,
CW.
you're right, you
Okay.
may do the CW to get
Yeah.
this.
And then that gives
Okay. Okay, yes, sorry.
Is that not correct?
It is, no, you're totally correct.
Okay, yeah, very good.
So yeah, one of the things you can do, if you don't get the basic with honors, you can do one of two routes. You can retake your basic test to try to score the honors, or if you do a CW test or the advanced test, you get access to the HF privileges. So the only person who isn't allowed below there is just basic people. But yeah, absolutely correct. Sorry, it was the original way you said it came out.
Yeah, no, I was just, it was going around, because before I got this book, I had an older version from the 70s.
Oh, okay.
And I can see the similarities. The pass was 60 and the honors was 75. Now the pass is 70 and the honors is 80.
Yeah.
I can see the correlation, between the two. Yeah.
All right. Next question. So this is from the appendix. Okay, these ones, yes. So if the power output of a transmitter is increased by 4 times, how might a nearby receiver's S meter reading change? Here's the first and funny thing about this. S meters are pretty bad. They have to be calibrated to work correctly, and most people don't calibrate them, so this is mostly a theory question and not actually a practice one. But you should know it if you read Appendix 1.7, and you remember what Appendix 1.7 is.
I read it, I don't remember. I was doing the math instead of that.
Anyone?
It's A or B, right?
I would say A. I would say
Approximately
A.
based by
hopefully.
4 years.
So, okay, hands up for A. 1, 2. Hands up for B.
Oh,
1, 2, 3.
2.
3 on 2. Okay, what do we get? Yes. So it's because it's in decibels. So the S meter measures the microvolts measured on an antenna in decibels. And again, just memorize the answer, don't actually understand.
Didn't it say in the book from what I read that each company has different ways of calibrating their own meters too?
Yep.
So
S
there
meters.
is no set way, really? Is that right?
This is very true.
It's very true, yeah.
Number of microvolts of the antenna and so on.
Yeah, an S meter, unfortunately, it's a really... There was
Just a
supposed to be
relative.
Yeah, exactly.
Just so basically one person's stronger than the other person or whatever, right?
Yeah, exactly. So if you see somebody who has, S9 and you see somebody who has S3, you know that the N9 is much higher in terms of signal
Yeah.
strength than the 3, but exactly how much you're calculating it. No.
Which doesn't necessarily mean they're closer,
No, yeah, exactly.
because it could be on a portable or whatever, right?
And if I could just, when the power went up, obviously it's not going to decrease. I mean, just so and I found a lot of
Just common sense.
a lot of the answers you can say, okay, it's definitely not those.
Yeah.
So now you've got a 50-50 chance of getting it right. You just
That's
take a
right.
stab at it, right?
That's right.
Okay, again, back on the S meters. There are only 2 questions on the test, so if you only get one of these 2 theoretically, hopefully. So, by how many times must the power output of a transmitter be increased to raise the S meter reading on a nearby receiver from 8 to 9?
B.
B? Alright. Alright, let's go to the answer.
That's
Yep.
number 4.
Yep. And this is okay. Next. I mean, technically they're not lying. If you go up by 1 S unit, you will be from S8 to S9.
Yeah.
So
That's pretty cool.
if we go back, like,
Not gonna lie.
I was like, I mean, they're not.
It's almost so simple it's stupid.
It's sick. Yep.
Yeah.
So anyway, these are the only 2 S meter questions.
Oh,
Thankfully,
that's
we're
good to
past
know.
them.
Yeah.
Yeah. But all right, moving on. 2 slides. Perfect. So here we go to Q codes, and we get to go through all of these, and hopefully you've all got them memorized. What is the meaning of this Q signal QRS?
I know
Send
this
more
one, I know
slowly.
this one.
We got send more slowly, so number 3.
And more slowly.
Yeah, all right.
Yeah.
Perfect. All right. And again, for anybody who's trying to come up with mnemonics or something, receive slow is kind of one of the one I use. So, all right, QTH.
My location.
Yeah, we're okay. Well, I think we'll blaze through these.
And H for home.
Yeah. So I've got headquarters, but home exactly. Yeah. So transmission headquarters is what I use, or transmission home.
I found those things you sent out really handy.
Okay, excellent.
Yeah.
So if anybody has better ones, by all means, feel free to. Yep.
QRP. I thought that was what's your location?
Reduce your power.
This is reduced power.
Power.
Yeah.
P for power.
Yeah.
Yeah.
What's the one for increasing the power then?
Oh,
RO.
QRO.
Yeah. So.
Thank you.
Roar.
Yeah. Roar, exactly. Yeah.
I remember. Yeah.
Perfect. All right, next one. What is the proper Q signal to use if you see a frequency in use before transmitting on CW?
I didn't study the. I think it's QRZ.
Steve. QRL's busy with that.
It's number 2.
All right, go for it. It's Q, number 2.
URL.
Yeah, it's number 2.
That wasn't a mnemonic for that?
You don't see that.
Receive
unless you use
lots,
Morse
yeah.
code on the
Yeah,
side
so
of the
I mean, this is an example of like you don't have to know Morse code anymore because you're not tested on it, but they're still requiring you to remember these obscure things. For anybody who read all the way down the list, you probably noticed that there's like, oh, how many telegrams do I have?
Yeah.
I would like to cancel telegram number 3, please. It just.
I did.
Exactly. If anybody starts asking you to take down telegrams, tell them to go away. But yeah, so it's because it's busy. Receive lots is kind of the way you'd remember it, but again, it's yeah. The signal QRN means.
I know.
You know it? What is it?
It's the treble by static.
Trouble with static? Okay.
Yeah. No.
Is it-
Yeah.
is it-
Okay. Go for it.
Oh, you
Trouble
got
with
it
static.
right.
Yeah.
All right.
So next one. And it's receive noisy.
Easy.
So the way to kind of, I broke it up is R's are receives, S is station, and T is miscellaneous. So, and then there's a couple that you have to remember that are weird, but for the most part, you can kind of work with that. The Q signal indicating that you want the other station to send more slowly is RS.
Yeah, QRS, yeah.
All right. Perfect. Yep. So remember, receive slow.
Yeah.
So,
Or receive slow.
all right. Who is calling me is denoted as the Q signal.
Oh, let's see that.
It's calling me. Q signal. QRM.
QRM.
Calling me.
I think.
Next one. It's QRZ.
I see.
So, next one. Anybody visited QRZ.com?
No.
No? Okay, you should. So, QRZ is just kind of one of the websites a lot of hams use to find out who's calling them or who they're talking to. So you type in a call sign that you're hearing and it'll bring up typically their name and address if it's available.
Or if they're legit.
Well, exactly, right? And I mean, I guess that's technically one way. You can also put up a picture of yourself on the site if you sign up for it. They have a paid version that you can get a website if you really want on your call sign, but it's just one place that, among many, that you can look up call signs with. So, the Q signal, which signifies "I will call you again," is. Oh man.
QRT.
QRT?
Yeah, QRT, isn't
QRX.
it?
Exchange. So, yep, receive expected.
Expected.
So,
QRT.
yes. Okay, so we're done. We're done. This is all of the Q codes that are on the test. Technically, you have to know them all. That is it.
That's
That
not
is
bad.
all of them. But I mean, this will be the place that you'll be like, and I got that one wrong, and I got that one wrong,
Yeah.
because it's entirely arbitrary. So, moving on.
Sorry.
Yeah, I'm so sorry. All right. How much voltage does a standard automobile battery supply?
12 volts.
12 volts. All the car guys are just like, yep. Yeah, 12 volts. For anybody who's confused, 9 volts are the little batteries, or you can get a little bit bigger ones. And 120 and 140 are wall current, or wall voltage, not current. But, all right. Which component has a positive and negative side? A battery. Yep. So it's one of those things, if you didn't know what all the other ones are, but you knew one of them was correct, like battery, you're good. Yeah, potentiometer is just another name for a variable resistor, for anybody who didn't know that. So, all right, a cell that can be repeatedly recharged by supplying it with electrical energy is known as a
Memory cell.
memory cell?
Or sorry, storage cell, sorry.
Storage cell. Storage cell.
Yeah.
Right? Yep. So yep, primary or one use. Low leakage means that the cells lose charge more slowly when not in use, and memory cell is not a thing. Except like maybe in computers. All right, moving on. Which of the following is a source of electromotive force, EMF? Okay, go for it. So it is lithium-ion battery. EMF is just another fancy name for volts. So is voltage potential, voltage difference, potential difference. Everybody likes to come up with a new term for things that are already named.
Potential difference, isn't that Ohm's law?
It is. It's a part of it, yeah.
Where it takes 1 volt to force 1 amp through a resistor of 1 ohm?
Yep, that's correct.
Yeah, okay.
And if I could just mention that E and V can be very confusing. They're the same thing.
Yeah.
Yep,
yeah.
exactly. So
That's what I found. A lot of these, they're not very consistent, are they?
No.
Not
No.
as logical as you would think.
no. So I mean, it's basically a problem with. I mean, when everybody was coming up with learning the ways that electronics worked, everybody was just guessing and running like mad. So
Couldn't you put P in that?
P for power and watts, W, same thing.
Yeah.
We were talking about this at Tim Hortons, and it's very confusing, and it doesn't have to be.
No.
They just got to stick to one symbol, and that's it, and not
Yeah.
keep having several symbols meaning
Yeah.
the same thing.
And when you get the 2 textbooks, that are one's done with power, one's done with electrons. So you got the reverse concepts.
Yeah.
yeah. Oh, man.
Alex, just before we move on,
Of course.
when you were going through the Q codes, there was an awful lot more that it said you've done them all, but they're like all the common ones that I know, none of those appeared. So
Are there
Yeah, like-
there are others.
No, yeah. There are other.
Yeah.
Absolutely, there are other Q codes that are in that
26, I
list.
think.
Yeah, but
Yeah.
from the actual exam, those are the only questions that currently deal with them on there.
I
Yeah.
didn't know that they're only limiting you to, you only got to learn those few.
So
It's a lot of
technically,
time.
technically at any time they can update the bank and add any question they want. But at current time, those are the only ones on there.
Yeah, so,
So-
the current ones are RA, RO, RZ. What was that list?
Oh, probably best to pull up at the end of this.
Oh, okay.
So
You're gonna put
They're
it on
available
the-
online.
this will be on the online portal, yeah. So it'll be under
That's
week
what's driving
one
me crazy
slides.
I think
Yeah,
it's like,
so.
I think I was studying one today, I think there's like 20 to 30 of them in the actual book, and clearly you don't need to know all 20 to 30.
Yeah, but that's what
Yeah.
Yeah.
when you said that, it was all of a sudden, okay, which one did he say? I could put star beside them.
Yep, yep,
So
no,
you use
absolutely.
figures for the resistor code.
Anyway, keep rolling on
Okay.
forward. An important difference between a conventional flashlight battery and a lead acid battery is that only the lead acid battery can, or
Say what?
Will be
See,
recharged, repeatedly recharged.
Repeatedly recharged.
repeatedly recharge. Yep.
Absolutely, yeah.
So yeah, all batteries have 2 terminals. No battery can be completely discharged. There's always some little potential that's left. And all batteries contain an electrolyte. So,
Oh, thank you, sir.
next question. To increase the current capacity of a cell, several cells should be connected in
In
Parallel series? series?
Yeah.
Cool. So it's in parallel. So when you compare, so next one. Yeah. So series increases the voltage, and parallel increases the actual capacity. So if you connect them in series, you'll blow things up, and if you connect them in parallel, you'll be able to power it for longer. All right, next one. To increase the voltage output, several cells can be connected in.
Series.
Exactly, series. But okay, next. They have resonance, series, parallel. I mean, they're making up terms at this point. So, but that's another example where they've done that sort of thing. They have one version and then they've just changed the question, and it's basically the exact same concept. So, lithium-ion battery should never be short-circuited, recharged, left disconnected, left overnight at room temperature.
Short-circuited.
Short-circuited, exactly. Because lithium battery fires are not funny. No. Water makes them stronger. You need a Class D fire extinguisher, and most fire extinguishers are only ABC. So, lithium fires are not something you want. If you ever hear somebody who's like, "Yeah, just connect the battery terminals," don't do that. All right. If your mobile transceiver works in your car but not in your home, what should you check first?
Power supply.
Power supply sounds like a logical answer. Power supply, exactly. Again, if it works in one power supply and not on another, it's probably the power supply. Just basic debugging. Your mobile HF transceiver draws 22 amps on transmit. The manufacturer suggests limiting the voltage drop to 0.5 volts, and the vehicle battery is 3 meters, 10 feet away. Give the loss below that current. Which minimum wire gauge can you use?
Holy smokes.
Oh boy.
This is one of those ones we're actually going to get to.
That's right out of the book, and all right.
No, it's not out of the book. Okay, let's break it down, right? So we've got these different gauge numbers, right? Gauge like 8, 12, 14, 10.
I remember
right?
now, the higher the gauge, the thinner the wire.
Exactly, yeah.
Thicker the wire. Oh, sorry. The larger the number, the thinner the wire, yes.
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 Bigger the number, smaller the wire.
Absolutely.
Yeah.
Basically the way it is, like the bigger the number, the more you get per dollar. So we've got 0.5 volts per meter, 0.01 volts per foot. Okay, so we have to go 10 feet, right? Which means that we're experiencing a loss of 0.5 volts per meter. I guess the first thing to do, go to the answer. Okay, so it's 10 gauge, which gives us 0.07 volts per meter at 0.02 volts per foot. Okay, so we go to the next slide. Let's break this down. The voltage drop calculation is simply the length times the voltage per unit, right? That's the voltage per unit you lose.
12-meter gauge?
Yep. So using the 12 meter gauge as an example, right? 10 was the correct gauge, but using the 12 meter, right? It gives you a voltage drop of 0.11 times 3, right? Because if we're go back, we have to go 10 feet, right? And we've got a 0.11 volts per meter, or 0.03 volts per foot. Oh yeah, I guess, forgot I had pens. Okay, so we've got, sorry. We're gonna do the 12 as an example. So 12 as an example. Pick a better color.
Yes, please. Thank you, sir.
So 12 gauge.
Sugar milk. Oh, black. Yeah, that's fine. Thanks.
UGE.
Thank you.
Thank you.
I'm fine. I'm just gonna have black.
All right,
Yeah,
gives
black,
us. I just need the 0.03 volts per foot, and then we have 10 feet we have to go. Okay, so next slide.
So what's the formula?
So we just take the length and multiply it by this. So we take 10. We get 3 length times volts per unit length. Okay, we gotta go 10 feet. We multiply by 0.03, right? Gives us voltage drop of. So then multiplying by 11. The larger the gauge number, the smaller the diameter, the lower the cost. Our best is 12 gauge. Bang, goodbye. Once. Okay, so we're doing 10 times that, which gives us 0.30, not 0.33 volts, right? So on 12 gauge wire, for example, we should experience a drop of 0.3 volts, all right? Unfortunately, it's pretty poor in order to explain that, but the problem is essentially, if we do that, that gives us, go back to the question. So the manufacturer suggests limiting the voltage drop to 0.5 volts. So the actual thing has to be less than 0.5 volts for your distance of wire. So 0.3 volts technically makes it under, and we're totally good. But the thing is it just has to be under in some particular way, right? But they specifically tack on this word right here, right?
What was your answer?
So 0.3 volts is the loss on 12 gauge wire. Oh, sorry, go back.
Okay.
Yeah, on 12 gauge wire at 0.03 volts per foot, we have to go 10 feet.
So we're doing
10 multiplied by 0.03 volts.
0.03 volts.
Yep.
Yeah, 0.3, yeah.
0.3 volts, and we just have to be under 0.5. But then they say minimum wire gauge, which means we have to start working down here and then go 10 and then 12 and then 14 until we find one that meets, right? If we do 10, we get 0.2002, right, volts per foot, which gets us to 20. Is that correct? 10? Yeah, 0.02. So it gets us to 0.20 volts, right? Which gives us a total of 0.2 volts, which is still also less than 0.5 volts loss over the run. It's long and complicated. All you have to really remember, you multiply this number by this number, so long as they're in the same unit, so this is feet, that gets you the voltage drop across the wire, and then you just have to find the smallest gauge in terms of number, right? So 8 wouldn't work, for example. Or, no, sorry. 14 wouldn't work.
No, it's too high.
Exactly. 12 would work. 10 would work. So I don't know why.
10 is the best.
Yeah, got it. Thank you very much.
Get the
Smallest
last one.
wire.
Yeah, that's the smallest you can go, yeah.
Hmm.
0.2.
So go to the next one.
12 is the smallest.
12 is the smallest gauge?
Yep.
It would work. Our best is 12 gauge, but Industry Canada wants the word minimum.
It is minimum. 12 is minimum. Go back again.
Okay.
So that's, they're wanting 10?
Yeah, they want 10 feet.
Yeah, which is
Which is thicker-
0.02.
Which is thicker wire than 12.
Yes.
It is.
They asked for minimum. 12 is minimum.
But wouldn't 8 be minimum then?
Well, it's minimum in size. So that's confusing. It is confusing.
Yeah.
Yeah.
Okay.
Yeah, you could do it with 8, because that's the minimum size.
Yeah.
Yeah, minimum.
Yep.
So you got,
Alexander,
are you
you're
talking
talking
Can you have two?
Yes, I would love a glass of water. Yeah. Okay, so I
they're
guess-
right. They are right, because they're talking about wire gauge, not wire size.
Okay. All right. That's the answer they give as the correct answer. How they get to it, I'm not exactly sure. I'm pretty sure they're wrong, but I can't argue with them because I'm not the one writing the test. So.
It's just like we're at Tim Hortons again, isn't it?
Exactly, except this time I'm sure they're wrong. I want an actual explanation as to why. So there are a couple of questions like this that you will spend hours working on. If you just memorize those ones, it'll get you like through them no problem. So if you just remember that it's the 10-foot one or the number 10 wire, you're good. All right, moving on.
Yeah, 10 gauge.
10 gauge.
Absolutely.
Exactly. How do you find a resistor's tolerance rating? Oh, this one's great.
The colors on the coat.
The colors, right? They're reading by the color. Okay, so move on.
Black, brown, red, orange,
I can't even remember what that is.
gold is in there somewhere.
Silver.
Yeah.
Okay, so for the resistors, the way to remember it, you'll check it on the website again, right? You got black, brown, which are the two bottom ones. You got Roy G. Biv is an easy way to remember the colors.
9-0 Denver.
9-0 Denver. Oh,
Yeah.
so I think Denver's winning. Anyway,
Well, if he doesn't let him win the first quarter, they won't let him play the second.
it's true. All right, so we've got black and then brown because we're going dark to light. All right. Then we have Roy G. Biv, which I'll come back to in a few seconds, but that's how you remember all the rainbow colors in order. And then you finally get to gray and white. And gray is 8 and white is 9. So we've got black, which is 0. We've got brown, that's 1. Red, orange, yellow, blue, green, indigo, violet. Roy G. Biv. I will write this down. Which? No. I don't want to stab you there with that marker. So,
Roy
G. Biv.
G. Biv.
So we got red,
Red,
orange,
orange, yellow, green. What's that?
so this is blue.
Blue, yeah.
I is indigo, just because Roy G. Biv sounds good and Roy G. Biv doesn't. So indigo technically is in there, but nobody really counts it. We got blue and then violet, which is just another name for purple, if anybody's familiar with that term. This is one way to remember it.
Slate white.
Slate white? Okay.
8-9.
Roy G. Biv.
Roy G. Biv. The other way you can remember it is red, yellow, and blue, And then remember your composite color addition rules. So
Roy G. Biv is good. I like that.
okay. Yeah, the other way, as I said though, red, yellow, blue, and then red and yellow makes orange, yellow and blue makes green, blue and red makes violet, and then you just remember because it goes red. Anyway, you can remember either way. Roy G. Biv is great.
What's the one in the book or something about your business will go south or something?
Yeah,
Oh,
I
yeah.
was just thinking that. I just had that memorized. Oh. It's right near.
Where it is.
Yeah,
where it is.
Got a brain fart.
Better be ready or your great big,
Yeah, it goes out west.
big venture goes west.
Yeah.
So
I
again,
remembered that.
whatever you can memorize it with, that's the way to do it.
No,
That's
this
right.
is good. I like this Roy G. Biv.
Okay.
It's in there now. Yeah.
All right. Anyway, as for the actual answers we had before, Baudot codes are a way of encoding letters that predate ASCII or anything like that. They use 3 dots to represent all the 5 dots. They use 5 dots in the particular order they come in to represent.
I'm sorry, I shouldn't do that.
Nobody uses it anymore. Nobody. All right.
The radio teletype actually does.
They.
But nobody uses that.
Okay, nobody uses it. I was like, nobody uses it. All right. An ohm
We're
meter.
talking redundant here?
Oh yeah. I mean,
Absolutely, eh?
yeah. An ohm meter reads.
But the book doesn't have indigo. That confused me.
Yeah, no. So again, indigo is not in there.
It's
I
off
mean,
indigo.
nobody really uses indigo anyway.
Okay.
I've never been like, wow, you have a beautiful indigo wall. Like,
Excuse me.
Oh, thank you.
You will.
so
Guys only know primary.
an ohm meter is what measures resistance.
We're all going.
Not an ammeter. We've got Theven's theorem for resistors. Just know. Okay, so Theven's theory for resistors is how you calculate large-scale resistor networks.
Cookie Mr.
Not on the basic test. Not even on the advanced test. We're talking like 4th level university engineering courses, kind of. Just no. No, you will never need to use theorems. No, just.
Thank God for that.
Exactly. Well, because you start using calculus at that point, because you have to calculate integrals, and oh man. So.
Thank you.
All right, next one, whenever we can.
Hold on.
Of course.
Alex, can I offer you a cookie?
Oh, I'd love a cookie. So.
Coffee, Alexander?
I'm actually good on coffee, so.
Alex, this could be confused to black if you didn't know. That's
Yes, if
the
you
only
didn't know.
thing.
Yeah. So you just have to remember that Roy G. Biv just colors the rainbow, and then just remember black is not a part of the rainbow, nor is gray. White,
Right.
not really, and brown again, just not in there.
Jeffrey Biv is good. I like it.
Good.
So, what do the first 3 color bands on a resistor indicate?
Resistance. You know.
Yep. Go for it. So the value of the resistor in ohms. All right, remember that the first 2 are the numbers, the 3rd one is the multiplier, and the 4th one is tolerance, right? The material color is somewhat of a case coloring thing, so beige ones are carbon film, blue ones are metal film, nobody cares. And watts are not recorded on it, so it's determined by the size of the part, and you'll get it when you purchase it. If you're purchasing 2-watt resistors, you'll know. So.
And if you are working on your wartime radio, it will be body, tip, and dot, not bands. Body, tip, and dot is the 3 colors. You won't see the bands on an old resistor.
So say again, Jeffrey's body,
Tip and dot. The
Tip
body of the
and dot.
resistor,
right?
then one end is a
Yes.
big blob,
The tip.
and then a dot in the middle, and those are your 3 colors.
Oh, that's really cool.
Yeah.
I didn't know that.
I think that what staying with that subject, I guess where the radio was sat for the past little while in Dad's basement, because the resistors are cardboard, they
Carbon
are,
resistors,
no, the
the
outside.
capacitors you talk
Oh,
about.
sorry, the capacitors
Yeah, okay.
are cardboard,
Yeah.
and you can't read what's on them.
Yeah.
It's kind of like a water
I'm going to
stick.
help you with this, okay? I just don't want you to muck about with it until I get there.
No, I'm not going to touch it.
Because it makes it, even a tube that has no numbers on it, if you know how to do it, you can sometimes read the number by, you just breathe on it and get the light in the right, and you can read the numbers on the tube.
Yeah.
Alrighty.
Oh yeah. No, I'm not going to touch it. No.
Perfect. All right. What are the possible values of a 100 ohm resistor with a 10% tolerance?
90 to 100.
90 to 100. 90 to 110?
Yeah, I think it's 10 to 100.
Okay. Go for it. So it's 90 to 110. So remember, tolerance is going to be plus or minus the value. And so, pretty straightforward. 10% of 100 is 10. So we get plus or minus 10%. Perfect. If a carbon resistor's temperature is increased, what will happen to the resistance?
If the carbon resistor temperature is increased, what will happen to the resistance?
Goes up.
It goes up.
Yeah, because of the heat.
Mm-hmm. So it will change depending on the resistor's temperature coefficient rating. Next slide. Yeah, it'll change. It'll go up, and resistance goes up. Yeah, resistance goes up. How much will usually be on the part sheet if you're buying really expensive resistors? There are some decent numbers you can work with online, but I mean, once your parts start getting hot, anybody's guess at that point. Especially because you already got some tolerance that your resistors have. Yeah, I mean, if you can calculate the internal state, good job, but it's not going to do you much. All right. A gold tolerance band on a resistor indicates the tolerance is
10, yes.
10. Go for it. 5.
Oops.
So next one.
We guessed
So
on that, didn't we?
Yeah.
20% tolerance is no band.
It's right.
Then silver goes 10%. Then we get 5% for gold.
Oh, I got it backwards.
Anybody remember what 1% is?
Brown.
Brown.
Yeah.
Okay. Yeah. Because brown is number 1 and red is number 2. And then from there, you jump a number and you go past orange and things start getting messy. Don't worry about that. You don't have to know any of it.
That is commonly used in multimeters, and that they've got to be dead on, absolutely dead on. Most circuits are not critical. But
No, yeah, most
those
circuits.
are.
Yeah.
Yeah.
Oh, and just another quick thing, Alex, that those resistors will be almost certainly out of tolerance on your old radio, because as carbon resistors age, they change their value.
Yeah. That's an
very
old
cool.
book that I got. 7.
7. All right, so we know it's not 72, right? So we know it's one of these in here. Okay. And then what does yellow represent as a multiplier?
4 zeros.
4 zeros, exactly. So then when we get 4 zeros, I'll break it down actually on the board. We have 2, 7, and then 0, 0, 0, 0. If we convert that using metric prefixes, we get mega or kilo?
Mega.
Mega?
Megos, yeah.
Yeah, 0.27 megawatts.
0.27. Well, remember what we have. We have 27 mega ohms,
Yeah.
270 kilo ohms.
170 kilo.
270 kilowatts.
Answer is 270 kilo ohms. So, again, because we got red, which is 2, violet, which is 7, and then we got 4 zeros, we're 10,000, right? So when we take 27 multiplied by 10,000, we get 270, and then kilo means we can take 3 zeros off the end, so we end up with 270. Another answer that would have been equally correct would have been 0.27 mega ohms, but we weren't given that option, so. All right, moving on. If an ammeter marked in amperes is used to measure a 3,000 milliampere current, what would the reading show? So this is just straight metric conversion from 3,000 milliamps into amps.
3.
0.3.
0.3.
0.3? Okay.
Not 3.
We get 3.
Off by just a little.
So because milli is 1/1000th, right? If we remember, it goes deci, which nobody uses. Then we have centa, and then we have milli, right? That's 3. So we move up the decimal place 3 points to the right. 1, 2, 3. We end up with 3.
Yeah.
So perfect. So there was a coffee break. Perfect. I actually like that. Here we go. More metric for us. How many microfarads is 1,000 picofarads?
There's a microfarad.
What's a microfarad? There we go.
That's what I'm asking.
That's fine.
0.001.
0.001 microfarads we have? All right, let's see the answer. 1 microfarad. All right, why? Okay, so everybody remembers the metric scale. We had deci, which nobody cares again. Then we have centa, then we have milli, and then we go micro, nano, pico.
Could I see the question again, please?
Of course.
How many microfarads, okay.
I don't even know where the microfarad is.
6 decimal.
See, we're not alone.
6 decimal
We're not
places
alone, eh?
to the left.
6 decimal places.
To the left. And the picofarad is 12 decimal places to the
Actually,
left.
here, so I can write it on the board
Places
for
to
us.
the left.
So if we have, what, 1 picofarad would be 0, 0, 0, 0, .0000000.
Upstairs.
Oh, just here.
Is there decimals in there?
The game?
No, so yeah, the 0.0.
Okay, it's just.
So this is the number of actual farads that 1 picofarad is. So we end up with milli, micro, nano, pico. 0.001 farads.
That's the furnace over here.
That's a picofarad.
See, 12 decimal places, and I said 12 zeros.
Yeah.
So, farad is a huge measure, by the way. If you ever see something 1 farad or 2 farad, don't touch. It will. So farads is a way of storing electricity in a capacitor, and a farad is like blow your heart out through your chest kind of amount of power. You won't see it on anything except like large industrial machines. So, for the most part, you'll see picofarads, maybe microfarads, nanofarads. You see microfarads?
Oh,
We use it in elevators all the time.
Okay, microfarads then.
Elevator timing controls.
Okay.
Relays and stuff.
In electrolytics especially.
Yeah, we use a lot of electrolytics.
Picofarads are little poofs that they use them for tuning to go across a coil, and then you would also have an adjustable capacitor for VHF work. I think.
Okay, yeah.
So
Yeah.
it varies tremendously, as you can see the number of zeros up there.
Yeah. If you want, I'll probably toss it up on the website now that we have this question up here, but I'll put a video up there where somebody like arc welds with a really big capacitor, so that'll be kind of fun. Anyway, moving on. Cool. The current of 1/4 ampere may be written as.
Oh yeah, that's good. 0.25. 250 microamps.
250 microamps? Milliamps? Alright, what do we got?
Third one. Yeah.
Yeah. So again, micro is 3 decimal points lower than milli. So, and 1/4 is 0.25. Moving on.
So wouldn't I go back to that?
Yeah.
Now? I mean, shouldn't that be the answer then, or 0.25?
No, because again, it's 1/4 of an ampere. So 0.25 amps would be correct, but for milliamps, we have to move the decimal point 3 places to the right, which gives us 250 milliamps. Microamps, it would be 250,000 microamps, because we get an extra 3 decimal places.
To the right.
To the right. Yeah.
I'm going to screw this up, I know I am.
Don't worry, don't worry. So, again, definitely go home. Go home once you can. Pull up this, maybe not tomorrow, but maybe the day after. Go through the slides again. The main thing is using memory recall. Learning it tonight, we're going over the questions, but if you pull it up again and try to actually figure out the questions again, that'll really increase the amount that you can memorize.
I found the videos you put up were really good.
Okay, yeah. So again, if you want, go through the videos.
Because it gives it from a different point of view rather than just, yeah.
Will you send me that?
Which?
Will you send me out your...
The link? Yeah. I can absolutely send everybody who's on the mailing list a copy of the link again to the online portal. So, all right. Name 3 good electrical conductors. So this is one of those ones where every single one is just going to contain one thing that's wrong.
Last questions, right?
Last, yeah.
This one? Yep. Right? So, wood, paper, and mica are all insulators.
Insulators, right.
So, all right, next one. Name 4 good electrical
Well,
insulators.
the one with the air, so paper and glass and air and aluminum.
This one?
No.
Nope.
Number 1?
This one.
The glass, plastic, and
Yeah.
porcelain.
Yep.
Air too as well.
Yeah. So interestingly enough, this one here, plastic, rubber, and wood, all correct, but carbon, if we go to the next slide, carbon is weird. In different states, it can take on different properties. It can be both an insulator or a conductor, but for Industry Canada's purposes, it is always an insulator. So that's also why carbon resistors talked about a lot, because they consider carbon to be an insulator.
Conductor.
Which?
It's a conductor.
It can be. So graphene and nanotubes are very good conductors. In fact, some of the best. So
We use graphite contacts, carbon contacts.
exactly, yeah. So that's what I'm saying. This is one of those places when you know too much, you start to become like, well, they're wrong. Well, yeah, it's weird.
In this example here, in this chemistry prefers...
Industry Canada prefers to classify it
Yeah.
that way.
As an insulator.
Yep.
Name 4 good electrical insulators. They've got it as a conductor.
Yeah. So they've got it as a conductor there.
Your next slide said it's an insulator.
Oh, geez. Okay.
Carbon is weird.
I guess, yeah, carbon is weird. Avoid carbon.
If that's the, if the other slide is the answer, then.
Yeah, one's contradicting the other.
Okay, so then I will fix this. This is my commentary on their questions and answers. So again, with the one with the 12, number 12 and the 10, and
Yeah.
I'll fix that one as well. So I now have 2 points to fix. But yeah, these are always my commentary on their question answers. The answer that I give is the one that is correct for the test. So I'll fix that. Moving on. Why do resistors sometimes get hot when in use?
Too much power.
Too much power, exactly. So, yeah, I love this one. They absorb magnetic energy, which makes them hot. Sounds like magic. Yep, so when any part limits or dissipates power, that is watts, it produces heat. So, what is the best conductor among the following materials? Aluminum, copper, carbon, silicon.
Copper?
Copper? Exactly. So anybody who remembers, aluminum is really bad, in fact 4 times worse than copper at conducting. So that's also why, again, when you had to replace your home because it had copper in, it's because when they heat up, aluminum will heat up faster than...
It's okay as long as you have the right connectors
Mhm.
in the box, but when they're not done properly, then it's a fire hazard.
Yep, yep.
Jackie knows about this, don't you, Jackie?
Alrighty.
Well,
So, oh, and the main reason we would use aluminum, by the way,
no,
is it's
no,
cheaper.
we just had a
So copper is pretty
practical
expensive.
inspection
That's what
done.
happened in the
Oh,
subdivision.
and had aluminum?
A little bit. We didn't actually
Yeah,
have to
she's
change
got
it.
both.
Didn't
Some
have to change it.
So, the reciprocal of resistance is conductance. Exactly. So again, conductance and resistance have the same thing, like hot and cold, right? They're just different ends of the scale. So when we're talking about conductance, we're saying these things are better at conducting. Resistance, these things are worse at conducting. And we could say the exact opposite. These are better at resisting, these are worse at resisting. So, a voltage drop means this is one of those ones you have to pick the specific answer that they're looking for.
Number 2.
That's exactly right.
The voltage which is dissipated before useful work is accomplished.
Nope.
So, before we go to the next one, I'll just explain. The voltage difference which is dissipated after useful work is accomplished is the voltage drop, right? The voltage drop is when you start at a particular point to another point, a voltage is developed across those two, right? So across a resistor, for example, you start at a particular voltage and it drops to another voltage. Through an element of wire, remember we had that voltage drop we calculated, the 12 gauge, 10 gauge?
Yeah.
There's a voltage drop through the wire. So in this particular case, after the work is completed, I mean, passing electrons through a wire is technically work as far as electrons are concerned, so that's the voltage we're looking at there. But there we go. And again, voltage changes in every part because of internal resistance. Everything has a resistance, from batteries to wires to also resistors. They're just typically very small, so we don't have to worry. The most common material we use to make a resistor is
Carbon.
carbon. Yep. Carbon film is extremely inexpensive resistor. That's all that needs to be said for our purposes. What is the word used to describe the rate at which electrical energy is used?
Current. The rate.
The power.
And we have
Power?
power. So again, next slide. Rate means over time, right? So current measures an instantaneous point in a circuit at an instantaneous time, right? How many electrons are in this particular section of wire, essentially. But the power over time, that is per second, how many electrons are being used to produce work, or joules, sorry, that is the power. So when we go back, specifically because it says describes the rate at which electrical energy is used, it has to be over time, so it's power. All right. Which electrical circuit will have zero current?
Zero current?
Zero current.
Closed.
Closed circuit?
Yeah.
All right, the answer is an open circuit. So, next up, answer. Shorts have theoretically infinite current.
Yeah.
Closed means it's
Yeah.
open.
No, I got it backwards. It's a light switch. Yeah.
Yeah.
No current going through.
Exactly, yeah. So because there is no connection from one end of a power source to another, there is no current.
Yeah.
So,
What's the word I want to say? There's no continuity.
continuity, yep. Yep. Which two electrical units multiplied together give us the unit watts? So this is Ohm's law again. Or
Volts and
Watt's
amps.
law. Volts and amps? Volts and amps. So again, P equals I times E, or pi. So. if a current of 2 amps flows through a 50 ohm resistor, what is the voltage across the resistor? Calculators.
Yeah, if I had the formula. 2 amps flow through 50 ohm, that's a resistor. 48.
40. Okay. So what we got 100. So if we remember, I mean, all you can do is multiply and divide. So you can't get 48, you can't get 52, and 25 maybe, but
Yeah, I was
All right.
guessing.
there you go.
2 times 1.
EIR.
Yeah.
All right, next up. How is the resistance in a DC circuit calculated when the voltage and current are known? Again, they do the same questions again and again, just different variations of the same topic.
They keep calling it all different stuff, which really confuses me.
Exactly, yeah. Try to
Direct
get in
current
your
is
head.
calculated by
Voltage current?
when the voltage and current are known.
Mhm.
So then the resistance equals the current multiplied by the voltage.
Survey says.
Well, you want to divide it. Son of a bitch.
So, so EIR, remember, E is voltage. I, we have, because, no, we don't have, right? So we have E and we have R, we don't have I. And because we have multiplication on one side, if we take that to the other, it becomes division. So then we end up with I equals V over R.
Do you know the trouble here?
Oh, you can draw the triangle if you want. Anybody want that?
The triangle, because then
Well, that's
then
what
it
I'm trying
shows
to
you the
think.
formula.
You just cover up the one that's
Yeah.
missing.
Yeah.
But you've got to remember that
doing
V and E are the same thing.
That's the same thing.
And P and W are the same. That's where it gets confusing.
That's what throws me.
Yeah. And it's
No,
the same thing.
I like the diagram, but it's the formula.
Can you use a darker pen?
Yeah, I was like, I don't know if I should keep going. There was
You know what? I got a picture
Where
of
you-
that. You want me to get it?
Yeah, this.
Picture of what?
What he's gonna write.
Oh, yeah. Right here.
Yeah. Here's one in the textbook.
Yeah, it's right here.
So,
I love
the
it.
horribly politically incorrect way to remember this is eagle looks down upon Indian and rabbit. It's terrible. Terrible, but it works. That's the way I remember it. I always remember eagles are always above, so again, absolutely awful, but it does keep a way of
I
remembering.
look at it as the poor injured raccoon.
Okay, an injured raccoon. That would work. So,
Yeah.
again, you just have to remember E is on top and then I and R on the below,
Yeah.
and you're good to go. Yep. So this is one of the ones that's on the site. This is the full circle that includes power law as well.
I'm not
And it
confused
shows you.
with that one.
It is, yeah. Don't try to memorize this one. It's quite a lot.
It's in color on the site, isn't it?
It is, yes.
And I think that's what buggered me because I'm colorblind, eh?
Oh, okay. Yeah.
Oh, geez, you're in trouble.
I think everybody in the club knows that too, right? That I was colorblind, and then Martha said to me, "All men are colorblind or something." Is that true?
No.
Don't look at me.
Oh,
No, yeah, I was like, not me.
Men apparently have a tendency to develop colorblindness.
Yeah, specifically red
Higher,
green.
higher
Yeah.
probability.
Yeah.
But all right, moving on. Because E equals I times R, so algebra implies R equals E over I. All right.
Men also go deft, according to my wife. Only on the side the women sit on in the car.
Calculate the value of resistance necessary to drop 100 volts with current flow of 0.8 milliamps. So if we know I and we know E, we're looking for R, which gives us. Also, by the way, feel free to write this on your test. When you get it, if you want, you can draw all the triangles just directly from memory as kind of a brain dump, and then you can keep referring back to it. So.
So it's E divided
You probably need a calculator.
I'm gonna guess 125 ohms.
125 ohms we have. Give you a few seconds there.
Yep, 125 ohms.
Answer? So this is one of those funny things. Next slide. You have to work in base units. So if we go back, we have 100 volts, which is in base units, but we have 0.8 milliamps, right? So we have to convert that to amps before we do anything, right? And then once we convert it, we see that we end up with 100 divided by 0.0000008, or three too many zeros, 0.0008, right? Which means we end up with a number that's 1,000 times bigger. So that's the only.
So the
quirky thing.
1.25. Yeah, the 125.
125 is correct, but if we go back, it has to be kilo ohms as opposed to ohms because we have milliamps.
Yeah, I didn't break it down.
Yeah, so that's one of the things they're going to catch you up with. A lot of them do that, where they throw a base at you for your second or third attempt.
If when I took my exam, just very quickly, there was two of us sitting at this kitchen table. This fella was 16 across from me, and I'm like 50, and he had finished way ahead of me, and Fred, who was taking the exam, and I said, look, I can't do it that quick. And the reason why I couldn't do it that quick is because exactly this. You've got to look at it, and then go over it. You see, because are they trying to trick you? And that's where this young lad made all the mistakes. He just did it too quick. He said, oh, I know that, and that's, you see, that's what you got to do.
It says in the book you got to
slow down.
Something in the effect of it must be in its lowest terms.
Yeah, so the way you would do that is base units, right? So if you have kilovolts or milliamps or micro ohms or any of that, you have to convert it to the base. So you have to first get rid of all of the metric prefixes, deal with it that way, and then you can take really large or really small numbers and try to shrink it to fit an answer. But definitely back to Jeffrey's point, take as long as you need. There is no legal time limit on how long you can take. I mean, probably don't take like 16 or 20 hours. The examiner probably wants to go home, but for all purposes, you can take as long as you need. So, all right. Oh, here we go. Okay, in a parallel circuit with a voltage source and several branch resistors, how is the total current related to the current in the branch resistors?
No idea, I haven't read that far yet.
It's the sum of the currents in each of the branches.
Excellent, yeah. Equals the sum of the branch, sum of the branch current through each resistor. So, it's talking about parallel circuits of resistors. Remember that current is divided by the branches, so the sum of the current in each branch is equal to the total current in the circuit. This is why we use parallel resistors, is to handle higher currents. So you're probably not going to be able to buy a 200 amp resistor. You can, but it'll cost you a lot. So instead you can use 4 50 amp resistors of higher value, but you have to calculate it out. So, total resistance in a parallel circuit is always less than the smallest resistance, depends upon the voltage drop across each branch, could be equal to the resistance of one branch, depends upon the applied voltage.
It's always less than the smallest resistance.
Exactly. Always, 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 always. So if you're ever working in parallel and you get a number that's bigger than any of them, something went wrong. So, yep. All right, two resistors are connected in parallel and are connected across a 40 volt battery. If each resistor is 1,000 ohms, the total current is Everybody stumped, or everybody just calculating?
I may be wrong. I was going to say 40 amps.
40 amps?
I'm wrong though. That's got me stumped.
Yeah, I'm going the other way. I'm going to go 40 milliamps.
40 milliamps? All right, let's see what we get. So we got 80 milliamps, right? So we're given E and we're given R, which means we need to divide 40 by 1,000, right? Which means we also know we're going to be working milli because 1,000 is way too big to end up with 40. But because we have them in parallel, we have to do one of each, and then we have to take the sum of both of the currents in either of them, right? So what we end up with is, go to the next one. We have I equals E over R, and thus we have 40 over 1,000, which gives us 0.004 amps, or 40 milliohms. I don't know why I put amps. I meant milliohms. No, milliamps.
Yeah, you're doing amps.
Yeah.
Then I put ohms in there for some reason. Okay. So we end up with 40 milliamps. Ignore this ohm symbol, that's incorrect. We have 2, So it's 40 plus 40. Remember, we add the current in each of the parallel circuits, which gives us 80. So, all right, next one. 5 10 ohm resistors connected in series equals. This is just testing whether or not you also studied the series section. We have the answer. 50 ohms.
Yeah.
Next one. It's just 10 ohms plus 10 ohms plus 10 ohms plus 10 ohms. You add them when they're in series, right? Same thing goes with inductors, and then capacitors work if they're in parallel. So you just have to remember the normal usage, and you just add them in that case. Nothing fancy. Moving on. If 10 resistors of equal value were wired in parallel, the total resistance would be... This is either going to take a really long time if we let you guys go at it, or if somebody knows the answer, it'll be over very quick.
10 times the resistance.
10 times the resistance? So it's the resistance divided by 10. We could, if you go to the next slide, yeah, it's just pointless algebra arranging at this point, because you've got 1 divided by the sum of each of one of each of the things, so then you can flip it and then flip it again, which gets you the resistance divided by the multiple. It's just pointless algebra. Again, you can go ahead and prove it if you really don't believe us, but yeah. All right, next up. 2 resistors are in parallel. Resistor A carries twice the current of resistor B. Oh, here we go. Here's the fun one. So this is the one that we spent 30 minutes figuring out whether or not it was correct.
No. Well, this is even worse.
No, this is the right one. 2 resistors are in parallel. Resistor A carries twice the current of resistor B, which means that... No, this isn't the one. This isn't the one. All right. Sorry, for a second I got you guys all worried. All right. The voltage across B is twice that across A. The voltage across A is twice that across B. The voltage has half the resistance of B. B has half the resistance of A.
Twice the current of the resistance.
Resistors have resistor A carries twice the current of B, which means that the voltage across B is twice that of A. And the voltage across A is twice that of B. Oh, isn't that just sticky boots? It's A half is the half the resistor of B.
Okay.
Yeah.
Oh, this one.
Yeah.
Yep, there we go. A has half the resistance of B. If we go to the answer, reason why. So we have E equals IR. So if E is constant, right, we're only changing what the resistance and current is, and I is twice that of R, that is I goes up, R has to go down, right? So if you have twice the current through something, you have to have less resistance. So, okay. If the voltage applied across 2 resistors in series is doubled, how much will the total power change? All right, let's go for the answer.
Yeah.
So it's 4 times.
That's what they say.
And we got to go through a bunch of math to get to this. So pull up the next slide and we'll...
It's pretty
come on over here.
straightforward. I simplified it, but you probably have already simplified it.
So if we recall that P equals I E, right? We can also rewrite that as P equals E I. Right? We all remember that multiplication works in both directions. If E is equal to I times R, right? So we have the power law and we have Ohm's law, okay? We can also write that I is equal to E over R, right? Because we can take the R onto that side, which is E divided by R is equal to I. So we have I equals E over R. Okay, so now we can write I in this equation here, the P equals EI, as this, right? Because I is equal to something, we can change that something out. So we can do this algebra, we can say P is equal to E times, and then we're going to plug in this I equation here, E divided by R. Because we're multiplying in, we can combine the 2 E's, and we get P equals E times E over R, or P equals E squared R.
For just a moment there, you said I was equal to E over R.
Mm-hmm.
And then you rewrote it as P is equal to times E divided by R. So you're using the same terminology, but you're giving a different passage.
Yeah, so the problem is we're working with 2 equations.
No, so is it E over R cannot be the same as E times R, or E divided by R.
E divided by R.
Yeah, but you said it was over.
Same thing.
Divided by or over.
Oh, it's the same thing?
Yes.
Yeah.
Oh, okay.
Yeah. When I say over, I'm talking in fractions, but
Yeah,
it's
because
the
you
same as
used the
dividend.
same terminology twice, and I just wonder.
Sorry, yeah.
Yeah.
So divide or E over is
Same thing?
Same thing,
Okay,
exactly.
very good.
yeah. Wait, we have equation 1, equation 2. We plug equation 2 into equation 1, work it out and simplify, and we get E squared over R. So
Do we do the brackets first then, is E over R?
yes, so because we're changing out in equation 1 the I just put it into brackets just to fully isolate it. But then because you have something multiplied in, you can just multiply it into both terms, cancel it out. Math, more math, and even more math. Or you can use this handy dandy wheel that explains that P is equal to E squared over R.
Now, I tell you, I'm going to be honest. I find this very confusing. So but I know what the answer is. So I did it my way.
Okay.
And
Yeah, go for it if you want the pen.
no, I'm just going to show you. Look. Okay. So you got 50 volts here, 50 ohms. 1 times 50 is 50.
That's right.
Okay. Now you've got 100 volts. 2 times 100 is 200. So if it's 200 there and you've got 50, it's 4 times. And like that's, to me, that's how it, if that helps anyone. You know?
Okay.
Yeah,
Do you wanna- you wanna look?
450s equal
Yeah.
the
So that's
200.
how I did it.
Well, that's simplified. That's simplified.
Yeah.
Okay.
That just simplified it.
I'm doing way too much algebra and
Well, you
Still
know,
in
and
university,
quite honestly, I think, I think Jackie, that's gone over your head, that one, isn't it? But this, you could get this one. This is piece of cake.
yeah. As I said, this is the most brutal thing you will see on the entire basic exam. So if this question, even if you want to get this one wrong, it's 1 out of your potential 20 you can get wrong. So it's not too
Is there
much. of a
20
worry.
questions like that?
No. This is the
You're allowed to
hardest
get
question
20
on the
wrong.
entire exam. So I mean,
Yeah, if you get 20 wrong, you can still get honors. That's
Yeah.
what he said.
yeah.
You know, do you remember going through public school, they had that same guy who was always in grade 3?
No. So again, yeah, don't worry yourself too much about having to understand all of this. Again, Jeffrey's way is much simpler, especially if you're calculating, you've doubled the voltage, calculate it out again.
Can we
But,
just see the question and answer game?
Yeah, of course.
So 2 resistors, double with
The first thing you do-
4 times. Yep.
You don't need 2 resistors. You
Yeah,
just use
no.
1 resistor.
Yeah,
So
that's-
that. You just simplify it, and
Yeah.
then it starts to make sense.
Yep.
Okay. Moving on.
1 sec.
Yeah, so this is the hardest bit of math on the entire basic exam, Instructor physics. Okay, which combination, change on the batteries? Alright. Alrighty. Which combination of resistors could make a 50 ohm dummy load capable of dispensing safely 5 watts? So this one seems complex on the beginning until you just start reading the answers. And then you see you have two 2-watt 25 ohm resistors in series. So they're telling you what the wattage of each resistor is. So there's not so much math going on here as initially we thought.
Sorry about that.
Sound like my John Deere.
Alright. Oh, Sabrina? Alright, I guess we can grab the answer on this one. So it's 4 2-watt, 200 ohm resistors in parallel. So when it comes to wattage, when they're saying safely dispense 5 watts, it just needs to be anything greater than 5 watts. Alright? Because it's in parallel, the amount of power that each one is taking is 1 over the number of resistors. Right? So if we're putting 5 watts through 4 resistors, that means each one is taking, what, 1 point something? Or another way of saying it is because we have 4, the total wattage they could take is 8 watts. Right? Because you add the wattage on each of the parallel. And then again, you just have to calculate the 200 over the 4 resistors. And the quick way of doing that is taking 200 and dividing by 4, which gets us 50. But the long way of doing that is taking 1 over the... Yeah, that's the long way. So, pretty simple. Moving on. Yeah, so this is the long explanation of all of it. Just skip, move on, I quickly explained it. The unit decibel, oh man, here we go, is used to indicate...
Ratio.
Ratio? Mathematic ratio? Okay, everybody seems to got this one.
Ratio, yeah.
Yeah, so it's a mathematic ratio. So again, decibels are useless on their own. They're not a unit. I mean, kind of a unit in terms that a ratio is a unit, but they're not like volts or ohms or amps. They don't actually mean anything by themselves. So it's specifically between two numbers. Moving on. Okay. A 2 times increase in power results in a change of how many decibels?
3.
3 higher, yep. Which? Exactly. So, power decibel at plus or minus 3 dB doubles or halves the value respectively. So in tens, they increase or decrease the value by an order of magnitude, right? That's pretty much all you need to know for the basic test. There is more theory behind it. You don't need to know more. Plus or minus 3 decibels, doubles or halves. And in tens, they increase or decrease the value by an order of magnitude. That's a multiple of 10. So, if a signal strength report is 20 dB over S9, what should the report be if the transmitted power is reduced from 1500 watts to 150 watts?
What the hell is an S9?
And that's the S meter, again. So,
No,
signal
we weren't
strength.
using that damn thing.
I'm guessing.
This one?
I'm guessing no.
Alright, let's go for it. That is correct. So because the power is reduced by an order of magnitude, that is, it's divided by 10, that's 10 dB. So, because dB work on a log scale, and engineers love logarithms. So yeah, 10 dB is an order of magnitude of power, an order of magnitude is a multiple of 10. So from 20 dB down to 10 dB divides by 10. If you want to go from 10 dB down to 0, which would just be S9, you have to divide again by 10, or 10 more dB. So, a local amateur reports your 10 watt, 2 meter simplex VHF transmission as 30 dB over S9. To reduce your signal to S9, you would have to reduce your power to blank watts. First thing, reduce the question. This is useless, this is useless, this is useless, this is useful, this is useful, this is useless, this is useless, this is useless, this is useful, this is useless. They're throwing lots of terms and stuff at you just to confuse you in this one. It's just the last question.
10 watts.
10 watts?
It's just a guess.
So it's 100 milliwatts, right? So if we go to the answer again, so it's 3 orders of magnitude. If we go back, we have to go from 30 dB over S9 to just S9. So we have to go 3 orders of magnitude, right? Which means divide by 3 zeros. So we go 1, 2, 3. We end up with 0.1 watt. We don't have 0.1 watts, so we obviously have to play around with the units. We can do 100 milliwatts, which will work. So, yep. A force of, here's a simple one. A force of repulsion exists between 2 blank magnetic poles. This is where technically a lot of them are correct. There's just one more correct than the others.
Yeah, like.
Yeah. So, I mean, yep, so yeah, opposites are correct. Yes, everything but unlike is correct, but like is more generally correct. So if we go back, a force of repulsion exists between 2 positive magnetic poles. Yes. Well, yes, because they're like magnets. Between 2 negative poles, yes, because, so, Industry Canada, it's like, you know. Alright. The permanent magnet would most likely be made from, you just have to memorize this one for some reason. Steel. Oh, wow. Everybody knows that. Okay. I guess I'm out in the dark. Yeah, just memorize that. Steel. The correct instrument to measure plate current or collector current is a transmitter is a
Voltmeter.
Voltmeter?
Transmitter.
Oh, transmitter.
A watt meter.
No, volt.
Oh, the correct instrument to measure plate current.
Current. Volt.
Plate current.
What are currents measured in?
Amperes.
Amps.
Pairs.
So we need to use an ammeter. Perfect. Ammeters measure current or amps. Ohm meters measure resistance, that's ohms. Watt meters measure power, or watts. And voltmeters measure voltage, or volts.
What, is there no correlation between never mind. No, yeah. That's one of those, no, the voltage is power, and so is current.
No, so
voltage sends the work for the current to do.
This is where they're being particular on their terminology. So power to them is specifically watts. That is over time the amount of work that can be produced. Voltage is a difference in potential between 2 points in a circuit. So again, it's because all of them are related to each other, but are different measures of the same thing.
Well, just for a quick question there. I want to talk about potential difference, or define the likeness of voltage, current, and resistance. It's just the same. The same has been said, but in two different manners. Could that not apply in that instance there?
Not particularly. So if we go back to the question. Yeah. So the correct instrument to measure plate current or collector current of a transmitter, right? So the current on a particular plate of a transmitter or the collector, they're talking about inside a tube, I'm pretty sure.
The plate's in the tube, the collector's in the transistor.
There we go, right?
Yeah.
So the actual current that they're measuring would be the electrons passing through a point, right? Power would be that passing through that point over time. So technically current is an instantaneous measure, right? Even though the way we measure it is over time. Electronics get weird when you really start to look at them.
Alex, if I might say.
Yeah, of course.
You see, that's overcomplicated because now you're thinking, what's going on here? But really, all is you've got to say, what's the instrument to measure current? That's it. As simple as that.
Yeah.
As soon as you know, what do you measure current? It's ammeter for current, it's ohms for ohms, it's power meter for watts and voltmeter for volts. That's all it is. It's pretty straightforward. Like a lot of these questions, they're almost trying to trick you a bit, you know?
They are. Yeah, absolutely. I mean, to their defense, they're trying to really test your knowledge, but really test your knowledge means let's make it as obscure as possible without losing the meaning.
That's why you've got to do it slowly. I honestly, I think anyone can, with a reasonable knowledge, can pass, but you've got to take your time because it's so obvious. If you're talking of current, you're not talking about volts, you're not talking about ohms, you know, it's pretty logical.
Exactly. Yeah. So here's one. The potential difference is measured by means of a... This is, again, they're trying to get inside your head, right? They don't mention specifically volts, they don't specifically mention watts, ohms. They're talking about a potential difference, and so the answer is...
Ohmmeter.
Ohmmeter? It's voltmeter.
Voltmeter.
They're talking about voltage potential between two different points in a circuit.
Yeah.
So...
But they don't say anything. They don't use the word voltage.
That's right.
Exactly.
Another tricky bit.
Yeah.
Exactly.
Run that question back.
So potential difference is measured by means of...
Potential difference is voltage.
Again, they're weirdly alluding to this sort of thing. They're like, well, but voltage potential is a term you've probably heard of, so we'll just throw the word potential in there. Yeah, exactly.
You're right, they are playing mind games.
They are?
Yeah,
Yeah.
and get you hooked into the...
Yeah.
And when the answer's obvious, if you take your time.
Yep. So,
Yeah.
moving on.
Says a guy that's going to fail it.
Oh, all right, so we made it. That's the end of tonight's thing. So we didn't cover, obviously, all of the questions on the basic that have to do with these particular sections. I chose, especially in sections where we were doing Ohm's Law, there's 10 or 15 questions on Ohm's Law where it's like, you're given voltage and resistance, okay? Voltage and resistance in a slightly differently worded way. Here's voltage and resistance in another slightly differently worded way. I picked some of the ones that really gave you, for example, when they throw different base units at you, when they tried to do things like, what's the potential difference? And you're like, what? Like, that's essentially what we're going for here, is just to give you an overview. The slides will be available online as soon as I get them in there in a PDF in a size that's smaller than a couple hundred gigabytes. For some reason, yeah.
I got to ask you a question. What is a scientific calculator?
Okay, so when it comes to calculators,
Texas Instruments?
I have one in my thing. Do you want me to get it?
I got one right here.
okay. Yeah. So the main difference.
Don't know how to use it, but I wouldn't want one.
Holster for that thing? I actually used to have that same one.
So a classic calculator you're probably familiar with will have something just down in this zone. This is the gray section. It'll have the numbers 1 through 10.
Let me see.
Yeah, of course. It'll have the numbers 1 through 10, multiplication, division, addition, subtraction. Those calculators are really cheap these days. I mean, I can pick one up for like $1 at the dollar store. They come embedded in rulers sometimes. So the step up from that is what we call a scientific calculator. It tosses in extra functions you may need. Specifically, it tosses in logarithms. It'll toss in a bunch of other stuff that you don't really need, like e and squares and all kinds of fancy stuff that maybe somebody in a high school math room needs. I mean, they got like cosine, tangent for anybody doing trigonometry. They have the pi. You can push a button to get the number pi on your calculator. The main one you might gonna want though is the logarithm button, and that's only when we're working in decibels. So if you memorize the equation for decibels and you're actually going to try and do those calculations, as opposed to using the shortcut that plus or minus 3 is a half or double, then you might want that. But otherwise, most calculators will do. So that would be the only particular sense that you would need scientific. Other types of calculators include, there's graphing calculators. Those are the really expensive ones you buy typically from Texas Instruments that have full dot matrix displays. You can put function. No, we don't need that. We use a computer. It's cheaper. There's also engineering calculators, which will have even more functions on it. Again, if it just has logarithms, buy the cheapest one you can that contains that. It's more than enough. So logarithms, yeah. And it'll typically be log, and then maybe like it'll have a little e underneath it or a 10. Those are just different types. But any other questions? Alright. Oh, yes.
Yeah, what do you
homework.
want us to do? That's right.
Homework. Okay, so for next week, chapters 4 through 6. 4 through 6 mostly starts to go into AC, right? So up until this point, chapters 1 to 3 will have taken you through just to the beginning of AC current. They'll tell you, there is AC current and it's different. Chapter 4, they really start to get you in on waves, the property of waves. And then by the time you get to chapter 6, you're going to start working on propagation. So how do atmospheric conditions affect the way your antenna is going to work. And that's what we'll be working on mostly for next week. Again, review the online content. Slides will be available as soon as I can get them up there. In a PDF, I also have a text version for anybody who wants that, who doesn't want to pull up a PDF reader. Again, practice Q codes and phonetics. Hopefully next week we can rattle off the particular sentence I put up. Again, with Q codes, we're going to go through those. Sorry?
Use license plates.
Yeah. Phonetics. If you're having a problem coming up with something, if you're sitting in traffic, start reading off license plates in front of you. They're fantastic. So.
Yeah, it's just when you put them in a sentence structure, you got to follow. You got to read the sentence and go along with it. But yeah, it's okay.